Uh, Good evening, everyone, and thank you very much for accepting my paper for this prestigious conference. My paper is basically an approach to reduce the performance requirement in NOMA resource allocation problem. Uh, I'm a master's in technology student from NIT Jalandhar, and it is co-authored by my mentor, Dr. Neetu Sood. Now, here is a quick summary of this presentation. First, we'll start with the basics of my topic, that is NOMA, its introduction, the systems, their transmitter and receivers, and how the resource allocation problem gets involved with the NOMA systems. Then brief literature review, which I've done, uh, which includes the related work which is done in this field. Then the objectives of this approach, this algorithm, methodology of this algorithm, its results and conclusion, and the future scopes along with the references. Now, what exactly NOMA is? So NOMA is a multiple access technique, and NOMA stands for non-orthogonal multiple access. So generally used multiple access techniques like FDMA or TDMA, which stands for frequency division multiple access, and time division multiple access, generally uses techniques like frequency multiplexing and time multiplexing in order to achieve the orthogonalization between the signals. But NOMA is fundamentally different from these all techniques. Since instead of time or frequency or code or space, NOMA uses two kinds of multiplexing between the signals. So either it could be a power domain based NOMA, in which the multiplexing between the signals or orthogonalization between the signals is achieved by multiplexing the signals in their power levels, or code domain NOMA, in which the same multiplexing is done in the code which is assigned to different signals or users. For NOMA, in transmitter side of the system, a very important encoding technique, which is known as superposition encoding, is used. And for the retrieval of this signal at the receiver side of NOMA system, another technique known as successive interference cancellation technique, that is SIC technique, is used to retrieve the signal of multiple users or the users which are there in the single channel. Now, in superposition coding, let's suppose there are multiple users which want to transmit their signal at a particular channel. So different power levels according to their power requirements are assigned to these different users. And then their signals are converted or multiplied with their power levels, and then added together to get a superimposed transformed wave, which then can be transmitted as a NOMA encoded signal for the purpose of communication. So here is a basic NOMA system. So let's suppose there are two users. One is a far user and one is a near user. We'll take user one as a near user, which is in close proximity of our base station, and user two, which is a far user. Now, obviously, the requirement of user one, the power requirement of the signal from user one is going to be lesser than the user two. So we allocate this power according to the requirement or the attenuation which is going to be done by the channel to the signal. Now, this different power levels which are calculated are then assigned to this far and near user. A near user gets lower power levels. In this power level, user one will going to be transmitting its signal, and user two gets a higher power level in which user two transmits its signal. Now, since they are getting allocated in uh, different power levels, and orthogonalization between the signals is achieved by using different power levels, simultaneously the time and frequency, which are the resources of this channel, can simultaneously be used by these both of the users of uh, the channel. Now, for superposition, in case of superposition in encoding, let's suppose there are two users present who wants to transmit simultaneously in a single channel at the same time. There are U1 and U2. So their power levels, let's suppose they are P1 and P2, which are going to be calculated according to the attenuation and noise susceptance of these signals accordingly. And they are, let's suppose, P1 and P2. Now, these power levels P1 and P2 are directly can be multiplied to their signals, and the amplitude of these signals will then be changed according to their power levels. These multiplied signals now then can be added or superimposed on top of each other in order to get a superpositionally encoded signal like this equation. Here is a block diagram of exactly what superposition encoding does to a signal. So basically, we have end users with their data. After their modulation, any modulation technique which they might be using can be done. Then the different powers are multiplied to their users channels, user signals, and then added or superimposed to each other. And then this superimposed signal, which is superpositionally encoded signal, is ready to transmit before conditioning, after conditioning, sorry. Now, at the receiver side of this system, there is a technique which is successive interference cancellation is used. In successive interference cancellation, let's suppose at the user one, which is near user, will receive the whole signal. It has user two's higher power signal also, along with its own required signal. So this higher power signal is easy to detect and easy to decode. So we'll condition our signal, and after this conditioning, we'll decode the user two's higher power signal first, and then this whole user two signal is subtracted from the received signal. After this subtraction, only the user one signal, which is the required signal for that particular receiver, is remaining, which then can be amplified, and after conditioning, the demodulation of that signal can be done. So this is a very basic representation of SIC. So let's suppose we have multiple users. So we'll decode the strongest signal first, which is the most easy signal to decode, and then we'll subtract from the overall signal, and then we'll repeat this loop until we get our original user signal, which is required signal. So till now we have seen the two users examples or something like that. If the number of users for a single channel increases, this also can be done. Like for example, if there are k users and want to transmit on a single frequency at a particular time simultaneously, then this can be done. The power levels of them will be allocated according to that, and the loop for SIC at the receiver side will increase according to the number of users. Now, like every new technique, we have different challenges along with NOMA also. So there is security issue, since as we discussed earlier in SIC, along with the original signal which is required at one's receiver, we have different users signals also, and we decode that signal in order to get the original signal. So this can pose a security issue. So a very good encoding for different signals is required in the technique. The second one is the inter-cell interference. So for lesser number of users in a single channel, it is a very good technique. But as the number of users increases in a single channel, the requirement of the power levels is also increasing, and the difference between these power levels, or the power ratio of these signals, are going to reduce. With this reduced difference between power levels, there is a slight chance or possibility that the inter-cell interference can appear between the signals. And the third and the most important is the resource allocation algorithm. How different users are going to get these frequency, time, or most importantly the power allocated to themselves when they are going to transmit in a single channel. So we have picked the third problem, the resource allocation problem, in this NOMA for our research. Since multiple users are going to share the same resources in a single channel and going to transmit their signal simultaneously, so the optimized resources needs to be allocated to particular users in order to get the most out of this technology. So when allocating the resources to different users, there are some aspects which needed to get considered. First is user pairing. Which users are going to get paired up for a single channel? There should be high difference between their distances from the base station, so that they can get a fairly large amount of separation between their power levels, which are going to get allocated to it. Now there's multi-user frequency scheduling and power repartition between the scheduled users, which is required when there is dynamic frequency allocation along with the power allocation between different users. And power allocation among subbands. If a single channel is going to get divided into multiple subcarriers, then the power allocation needs to be divided accordingly to it. Now, here is a brief literature review which I have done, and in order for my thesis, and these include some of the works which are closely related to this particular field. So first is Antonio Mesraccio and its team, who developed a user pairing scheme for NOMA system, which was based on NLP algorithm, which is nature-based learning processes. It is the algorithm is based on PSO, that is particle swarm optimization, and they achieved a user pairing which was linearly superposition. So when they used the SIC at the receiver side, there wasn't much distortion in the signal. In Krishna Murtikatian, they used a pricing scheme for the NOMA resources. They assigned a weight to each of the resources, and accordingly user had to buy these resources in order to use them. The methodology was based on Nash equilibrium, and they achieved higher utility by dynamically pricing each of the users. So it's like surge pricing in Uber or Ola cabs that we use now. So once there is a higher requirement of particular channel, the resources of this channel will get higher pricing for their users. So the users get divided according to it. Nakon Hao used a similar kind of approach, but used a two-step algorithm. Uh, uh, in step one, there is one penalty function method was used, and in step two, the allocation was done by using Dinkelpatch algorithm. Similarly, different energy efficient algorithms were also introduced and used by different methods, which are summarized here. Now, with all of these algorithms, as we see, there is always a trade-off between our energy efficiency and spectral efficiency. If you focus more on spectral efficiency, the complexity of the algorithm is going to increase. Definitely, it will affect the power requirement by the algorithm and the time complexity of the algorithm. Time taken by the algorithm to allocate these resources to particular users, which if the time required by the algorithm is higher, is not feasible in case of dynamically resource allocating base stations. So there was a requirement which in this NOMA system to use a particular algorithm which doesn't affect much of the spectral efficiency, but reduces the energy requirement of the system, as well as it doesn't affect much of the time complexity. It basically reduces the time complexity or whole complexity of the algorithm. So the objective of this approach is basically a generation of resource allocation system for NOMA by reducing the system requirements, that is the processing requirements, the clock frequency for users, and allocation. And so that by reducing the system requirements, it will be much feasible in the real-time scenario. Since NOMA is a better candidate in 5G, beyond 5G, and sixth generation of communication, most of these technologies are going to use a small cell technology. So their area of coverage is going to be smaller. So there will be a higher number of base stations included in the close vicinity. So by a company installing these all base stations in close vicinity with higher processing capabilities is not much feasible. It is not much cost effective. So we must reduce the system requirements somehow, and reduction in the code complexity, which in turn will result in lower time complexity and lower time usage. The methodology of this signal is as follows. So first, we need to generate a very basic simulation based communication environment, which includes one transmitter, one receiver, one channel, which the channel is just there to induce the noise and effects of attenuation for the signal. Now, the next step is to laying the problem on top of this simulation based algorithm, the NOMA system, and then there its modulation technique and the users. After that, the power level calculation for the different users sorry, power level calculation for different users for a NOMA system, and accordingly sorting of these users for a particular channel. Then user pairing and the resource block of NOMA of that particular channel. Then user pairing and resource block allocation to that particular users for particular channel, and their graphical representation and result generation. here is a flow chart which we just discussed. So we start with the user pairing. We club the users which are most further apart from each other. Then we calculate their power ratios. So power ratio is basically the maximum allowed power to transmit in a single channel divided by power requirement. So power requirement of this users, for calculation of power requirement of these users, we have used free space path loss model, uh, according to which the power requirement of a user is directly proportional to the distance between the transmitter and receiver. Uh, so as the distance increases, the power requirement by a particular user increases. So after this power ratio calculation, the optimization of this power ratio, or basically sorting of these users according to their power ratio, is done. And before pairing, it is seen whether this power ratio is optimum for that particular user in that particular channel is or not. If not, then user pairing is done again. And if yes, then this signal is further transmitted, further processed for signal encoding, its conditioning, and then uh, transmission. So here are some of the graphical representations of the results that we got. So for in this picture, there were three randomly generated users, which had their powers allocated. So if you see, the power levels between these three are allocated such that they won't be interfering with each other's data, as well as they will be not much further apart that we are wasting the energy of this particular channel. In this right side picture, these are the different signals which are generated for this particular user. So this is for user one, which is here somewhere in the middle. It got its power allocated, then user two and user three. So here is the performance processing power requirement by the allocation algorithm. So the left side gives the power requirement or processing power consumed by a conventional resource allocation algorithm, which you can see it was in the middle, it was using 100% of it. So basically the uh, machine on which this algorithm was running was a i5 5th gen at 2.2 gigahertz clock frequency, and it was using all the eight cores with 100% utilization. So you know uh, how higher the power consumption of this algorithm was. Now, the proposed algorithm uses somewhat average to 60% of this processing power, and almost if you conclude this, we have a 31% reduction in the power requirement of between a conventional algorithm and our proposed algorithm. This also, the code complexity is reduced. So this reduced code complexity is going to result in lesser time complexity, which in turn results in lesser required time by the uh, algorithm. And since we have a 31% lower power consumption, we have better efficiency from the energy POV. This algorithm is just an early stage. There are many things that can be done, which are future scope of this research. So first of all, as we discussed earlier, we have used free space path loss model for our power requirement calculation for particular users. Now, these free space path law models are not going to take the consideration, not going to consider the dynamics of environment in which the signal is going to get transmitted. So there is a requirement to replace this free space path loss model with empirical path loss models. By these empirical formulas, we can get much closer or precise calculation of these power requirements by a particular user. Then we need to increase this code's capability from single channel and multiple users to multiple channel and multiple users. And after the extending of these code, we need to use a better, less complex learning optimization algorithms. Generally, as we have seen in the literature review, most of the optimization algorithms used by these are NLP, that is nature-based learning process algorithms, like particle swarm optimization or beehive or genetic algorithms, etc. These are some of the references which I have used in this presentation and for my research work. And thank you very much.